All right, welcome to podcast 4.8. Continuing on with our types of reactions. This whole section is about acid-base reactions. And oops, there we go. And what we're going to do is just kind of go over the basics of what they are and do a little bit of acid-base stoichiometry and see how that works. So, if you were to look at a list of acids, you would see things like this: HCl, HNO3, H2SO4. And you'll notice that every single one of them starts with an H, right? And that's pretty common for acids. And so for our purposes at this point in the game of chemistry, we're going to say that an acid is simply a proton donor. So if you can imagine this breaking up, it's going to break up into an H plus and a Cl minus. This is going to break up into an H plus and an NO3 minus. Two H pluses and an SO4 2 minus. All right. So for our for right now, acids are going to be considered proton donors. Now for bases, at this point in our chemistry career, bases are going to have OH attached to them. All right. And so we're going to consider bases at this point proton acceptors, and they are usually going to accept an OH. Right. So here we go. What's the net ionic equation for the reaction of HCl plus KOH? It's always going to be some acid plus a base, and it's going to give you salt. Okay, and if you think about this, let me just erase this quickly. If you think about what's going to be the product of this double replacement reaction, basically, it's going to be KCl plus H2O. And so this right here is an ionic compound, and by definition, ionic compounds are salts, and then there's your water right there. So the net ionic equation is simply H plus OH minus gives you water. So this is our basic acid-base reaction. So pause the video right now and give this problem a try. Write the balanced molecular, total ionic, and net ionic equation. So let's see how you did. Well, first of all, I'm just going to write out HNO3 plus NaOH yields. Now this is a double replacement reaction, so I'm going to have NaNO3 plus H2O. Okay, so there's my molecular equation, and notice everything's 1 to 1 to 1, so that's kind of handy, right? So if I write a total ionic equation, this is going to break into some H plus and some nitrate. This is going to break up into sodium and hydroxide. This is going to break up into some sodium, or I'm sorry, this is going to be sodium and nitrate again. And then last but not least, there's some water there, right? All right. And then for the net ionic equation, we've got to get rid of the spectators, right? So what is the same on both sides? Well, here's our nitrate. That's the same there. That nitrate's the same there. Sodium's the same. So here we have a net ionic equation with a strong acid and a strong base. Pretty straightforward, right? Now that is always going to be the case when you have a strong acid, and at this point you guys know the 7 strong acids, and there's one of them. There's HNO, right? But we've got to be ready for the next thing, and that is weak acids. Because if you recall, a strong acid is something that completely dissociates in water. A weak acid does not. So if I were to write out this reaction right here, HCN plus KOH, all right, I would again do the double replacement thing. So I would get KCN plus water. Okay, so that would be the molecular ionic, or that would be the molecular equation. Again, everything's 1 to 1, so that's kind of handy. But here's a situation that's very important. When HCN is in water, so you add it to some water, okay, it does not break up into H pluses and CN minuses. All right. Most of the time it stays as HCN. However, we're reacting it right now with a very strong base, so that OH will rip off that H right there and make some CN. So if I'm going to write the net ionic equation, or actually if I were to write the, let's write the total ionic equation. This is what's going to happen. We've got HCN, again, not breaking up, right? Plus K plus OH minus yields K plus CN minus plus H2O. H2O. Now, something that's very important. Please note here, note that on both sides, the only thing that's the same are the potassium, right? So there's our spectators. So when you're looking at your net ionic equation, HCN is on the reactants, our product side, reactant side, and CN minus is on the product side. They're different, and so things that are different do not get canceled out, whereas things that are the same do get canceled out. So something to be very focused on when you're dealing with weak acids. It's absolutely critical that you memorize those 7 strong acids. So let's look at a little more into this. These reactions are often called neutralization reactions. Right there. And that's basically because the acid and the base kind of cancel each other out and make water. What we often use in chemistry, and you guys did this in your lab final last year, is we do titrations where we will take a known concentration of either the acid or the base and find out the concentration of the other one. Now, there's a couple words here that we don't really need to focus on yet, but the known concentration is the titrant. In other words, that's what we know the molarity of. And then the unknown is the analyte. And then the equivalence point for you guys last year was when we got that nice little pink color with phenolphthalein. So let's look at another thing here. We've got this 50 ml sample of calcium hydroxide, and it requires 34.66 milliliters of 0.98 molar nitric acid. What's the... Now these brackets right here, by the way, we haven't gone over this yet. These brackets mean concentration. And for our purposes, concentration is the molarity, right? So what we have to do, hopefully at this point you go, oh, well, we've got to find some moles, because we have a volume, and molarity is always moles over liters, right? So let's find some moles. Okay, I'm going to take that volume right there, I'm going to change it to liters, 0.3466 liters, right? And I'm going to times that by 1 liter is 0.098 moles. And when I work that out, that's going to give me, I've got that 0.068. Oh, pardon me, I'm looking at the wrong thing. I worked this out already. Boy, I'm so not a fan of this thing. All right. 0.0034 moles, right? Now, we need to find the concentration. So we've got to divide that by some liters, right? And the liters we have right here is our 0.05 liters. And that would equal 0.068 molar. Okay, and so there is your answer, right? So try one all on your own. Look at this problem. Pause the video, see if you could figure out what the concentration of the excess is. It's a little challenging, so give it a shot. Alright, let's see how you did. Well, the first thing I'm going to do is I'm going to write out my reaction. Now, it is an acid-base neutralization, so H plus OH minus yields H2O, right? The first thing I got to do is find the concentration of my H plus. So I'm going to take my 0.028 liters, right? I'm going to times that by the concentration, 1 liter, over 0.25 moles. And that's going to give me 0.007 moles of H plus, right? Now my next one, I'm going to take care of my OH, and I've got 0.053 liters. And again, I'm just taking those liters and dividing by 1,000, right? Or milliliters, I should say. And the molarity is 0.0320 moles, 1 liter. And that gives me 0.017 mole of OH. All right, now at this point, I've got to decide who's going to run out first. Well, hopefully you can see that this one, and this is a 7, not very well drawn 7. This is a 7. This one is going to be my excess, right? So if I just simply subtract 0.017, if I subtract 0.007 from it, I get 0.01 moles of OH minus. Okay, so that is what I have in excess, right? And they want to know the concentration. Well, hopefully at this point you're going, yeah, I know concentration is moles per liter, right? I've got the moles right here. So let me give another color just to make this a little easier to see. 0.01 moles of OH minus, and then I got to divide by the liters. Well, what liters do I have here? Let's see. I've got to remember it's a total solution, right? So I've got 53 milliliters and 28 milliliters. And unless my math is wrong, that adds up to 81 milliliters. So I'm going to make that liters. 0.81 liters. And then the answer I'm going to get is 0.123 molar. There you go. All right, acid-base stoichiometry. Again, like always, if you've got questions, we'll go over it in class. And see you next time.